Hello everyone, welcome to my EE140 tutorial video on normal incident waves. This problem is number 3 from midterm 3 from the spring 2020 semester. This problem states a high-frequency signal at 15.92 GHz is passing through a thick glass with an index of refraction equal to 4. The incident wave has an electric field given by E of I here. The questions ask, what is the reflected H field, the transmitted E field, the power in percent being transmitted all the way to the other end, the wavelength in glass, and the wave impedance in glass. So looking at question 1, what is the reflected H field off the first surface? So we need to find the reflected H field. However, this problem provides us with the electric field of the incident wave E of I. So to relate those two, we need to find E of R, which is the reflected E field. So I'm going to go ahead and write that, E of R, and we need to know the magnitude and the direction. So let's first examine what we're given looking at E sub I. So E sub I is going in the direction of positive x with a 1.5 magnitude, and the wave is propagating in the positive y direction. So let's draw a coordinate system to further evaluate this. If I label this x and this y, we can use the right-hand rule to determine the location of z. So if we point our index finger in the direction of x, our middle finger in the direction of y, so pointing up, then our z should be coming out of the screen, which is our thumb. So z direction, positive z, is going out of the screen. So looking back at our E sub I, we know that E sub I is going in the positive x direction. So we can go ahead and draw that in the positive x direction, E sub I. And the other piece of information this equation gives us is minus ky. So k is the wave number, and minus y tells us that the wave is propagating in the positive y direction. And we can evaluate this further by looking at a simple algebraic function. So if we look at f of x squared, we know that that graph looks something like this at 0. And if we modify that slightly so that the equation is x minus 2 squared, we see that the equation shifts to the right by 2. So this is a positive quantity even though inside of the function is a minus 2. So relating that back to our E sub I equation, if we have a minus ky, we can understand how the wave is propagating in the positive y direction. So we can go ahead and draw that as k. And now we can define a relationship between E and k through the cross product. So E cross H equals k. So if we look at our second right-hand rule, which is the bottom hand, we can point our index finger in the direction of E, which is also the direction of x, and our thumb in the direction of k, which is positive y, and our middle finger H should be going into the screen. So if we write that H is in, and we know positive z is out, that means H must be going in the minus z direction. And that'll be helpful for us later. So looking at our E sub R equation, we need to know the magnitude and the direction. We first can assume that E sub R is going in the same direction as E sub I, and then allow the reflection coefficient, which we call gamma, to either confirm it or correct it. So let's assume that it's going in the x-hat direction, and we need to find the magnitude. So we can find the magnitude by relating what we need to find, the magnitude of the reflected E field, to the magnitude of the incident E field, and relating that to our gamma, our reflection coefficient, which is equal to n1 minus n2 divided by n1 plus n2. So n is the denotation for index of refraction. And in this problem, it states that we have a index of refraction for glass equal to 4. So we go ahead and write that, n equal to 4. And we notice that we have surrounding the glass, we have air, which has an index of refraction of 1. So since we have 2 index of refractions in this problem, I'm going to go ahead and label air as n1 and glass as n2. So now we're finding gamma. I like to think about this as where the wave starts versus where the wave is going. And that's how I determine my n1 and n2. So if we look at this wave, we have an incident wave and it's traveling to the right. Once it hits this change in medium, some of it is going to be transmitted through the glass and some of it is going to be reflected backwards, the opposite direction. And that's the reflected part we're caring about. So first, our wave starts in air, and then it goes to glass. So the index of refraction of air, looking at gamma now, is 1 minus where our wave is going, which has an index of refraction of 4 for glass. And then we divide by the sum. And that gives us a minus 3/5 for gamma. So if we plug in minus 3/5 for gamma, we can solve for our reflected E field magnitude that we're looking for by multiplying gamma by our incident E field magnitude. So negative 3/5, and then if we look at E sub I, we know the magnitude is 1.5. So multiply by 1.5, and that gives us a reflected E field magnitude of negative 0.9. So if we plug that in, negative 0.9, and we're assuming that these E fields are in phase, so we're going to bring down the cosine, and then similar to E sub I, omega t minus ky. Now, we're going to pay attention to this part specifically. So minus ky, we see that also in the E sub I equation. However, now we're looking at E sub r, which is a reflective wave. So we're now propagating in the reverse direction, as we can see by our gamma coefficient. So this negative, once we multiply the x hat with 0.9, we're going to see that our wave is going, our E sub r is going in the minus x direction, and we can look at our minus ky and say that because of this, we're going to say our wave number k, our wave is propagating in the reverse direction, so we're going to make that a positive ky. So from here, we can find the values for omega and k. So omega is equal to 2 pi times the frequency, and the frequency in this problem is given by 15.92 gigahertz, and giga is 10 to the 9. So calculating that out, omega is 1 times 10 to the 11, and we're going to approximate that to be 10 to the 11. K, we can find through omega n over c, where omega is what we just found, 10 to the 11. And n, index of refraction for the reflective wave, is currently in air. We've reflected back and we're looking in air. So our index of refraction is 1 divided by the speed of light. So 3 times 10 to the 8. And that makes our k equal to 333.33. So if we plug in these values, for the reflective E field, we get a minus x hat, 0.9 magnitude, cosine of omega, which is 10 to the 11 t, plus k, which is our 333.33 y. And since we're looking at an E field, we know the units are volts per meter. So this is a very helpful piece of information here. We've now acquired E sub r, which is the reflective E field loop. So it's going in the direction of minus x, and it's propagating in the direction of minus y. So if we look back at our coordinate system and we draw E of r in the direction of minus x, so E of r, and then we look at k is now going in the minus y direction, and we use our right-hand rule, we see that our index finger in the direction of E and our thumb in the direction of K has our H field pointing in to the screen. And that's what we said earlier. So we can see that it's consistent and our H field is going in the minus Z direction. And that's what we want to find in this problem, is the reflected H field. So we said that's going in the minus Z hat direction. And now we need to find the magnitude. So the magnitude can be found from what we have, our reflected E field magnitude, and what we're trying to find, our reflected H field magnitude, and that's related to eta. And eta is eta naught divided by n. Eta naught is the wave impedance in a vacuum, which is 377 ohms divided by n, which is our index of refraction. And since we're dealing with a reflected wave in air, our index of refraction is 1. And so dividing that gives us 377 ohms. So plugging that back in for what we're trying to find, we get our reflected H field equal to our reflected E field magnitude divided by eta. So our reflected E field magnitude is 0.9 divided by eta, which is what we just found for 377. And that gives us a 0.002387, which we're going to round to 2.39 milliamp. So that's our reflected H field magnitude is 2.39 milliamps. So we'll take care of the units later. This wave is still in phase and the omega does not change. So 10 to the 11t. We are still a reflected wave, so we're propagating in the reverse direction. So plus ky, 333.33 y. And since we're now dealing with an H field instead of an E field, our units are going to be amps per meter, and we need to take into account the magnitude was in milliamps, so we're going to have a milliamp per meter. And this is our reflected H field. So the second question asks, what is the first transmitted E field in the glass? So this is number 1. Number 2 asks for the first transmitted E field. So we're going to find transmitted E field, and similarly to the process we were doing for E sub r and H sub r, we need to find the direction and the magnitude. So since these waves are in phase and we know E sub I, our incident wave, is going this way, to the right, reflecting and transmitting, second medium, reflecting, transmitting. That's the overall projection of this wave. So if we look at E sub I, it's going in the x direction. And since we're transmitting in the same direction as our incident wave, our direction is x hat. So now we need to find the magnitude. So the magnitude here can be solved for by dividing what we're trying to find, the transmitted E field magnitude, by the incident E field magnitude, and relating that to our transmission coefficient, which is equal to 1 plus gamma. And gamma is what we found earlier to be -3/5. So plugging that in, 1 plus a -3/5 gives us 0.4. Now substituting that back in to find the magnitude of the transmitted E field, we get our transmission coefficient times our E sub I magnitude, and that becomes 0.4 times 1.5 from E sub I at the top, our magnitude of 1.5, and that gives us a transmitted E field magnitude of 0.6. So we can plug that in, 0.6, assuming that they're in phase, 10 to the 11t, omega does not change, and minus ky. So here we're looking at a transmitted wave. So going back to our picture, we're no longer reflecting, we're transmitting, which means we're going through the material. So if we're going through the material, that's the same direction as our wave propagation for E sub I. So that means our wave propagation is a minus ky here. And since we're now going through a material, and if we recall when we solved for our first k, looking up here, we have our index of refraction equal to 1 because that was in air. Now we're trying to find our transmitted E field, and that is transmitted now through glass. So we have a different index of refraction, so we need to reflect that by a different k. So we're going to call this k2, and we can find it through the same equation, omega n over c, or we can use this equation, k2 equals our first k that we found times the new index of refraction for glass, and that's the one we're going to use. So k2 equals our first k, which was 333.33, times our new index of refraction for glass, which is 4. So our k2 is going to equal 1,333.32, and we're going to round that to 1,333. So if we go ahead and write that, 1,333 y And this is an E field, so we're looking at units volts per meter. And that completes our transmitted E field equation. So that's number 2. Number 3, how much power in percent is being transmitted all the way to the other end? Only consider single reflection / transmitted, no multiple bounces are being considered. So for number 3, we're looking for power. And specific to this question, we're looking about power being transmitted. So if I draw this again, the bottom, we have an incident wave traveling to the right. It encounters a first change in medium, and that was reflected by our gamma 1. Some of it's being reflected back, but we don't care about that here. We're looking at the transmitted part. So some is being reflected and some is also being transmitted. Okay, and then we hit this second change in medium, and then some is being reflected back, but we don't care about that, and then some is being transmitted. And this question asks how much power is transmitted all the way to the other end. So this is all the way to the other end. It's being transmitted. So if we're looking, each time there's a change in medium, we need to have that reflected by a gamma. So there's 2 changes in medium here. One is reflected by a gamma 1. So similarly, we need a gamma 2. So gamma 1, to remind us, we found as -3/5. And that was when we were going from air to glass. And now we're going from glass to air to find gamma 2. So if we write down what we have and what we want to find, we have gamma 1, which we found from going from air to glass. And that was -3/5, -3/5. And now we need to find a gamma 2, and that's going from glass to air. So gamma 2, if you recall the equation, was originally it was N1 minus N2. But the way we remember this is where the wave is starting versus where the wave is going. So we're now starting in glass and we're going to air. So if we reflect that in our equation, we're starting in glass, so that's N2, and we're going to air, N1, divided by the sum. So again, we're starting in glass, we're going to air. Glass, air. And that gives us a +3/5. So from there, we can use this equation, power transmitted over the incident power, and that equals 1 minus absolute value of gamma squared. So anytime we have a material change, we need to use this equation to reflect the power transmitted. So since we have 2 gammas, we encounter a change in material medium twice. So we need to add this, we need to multiply this equation again. So 1 minus gamma 2 squared. So we're going to call this gamma 1 and gamma 2. So we plug in the numbers. 1 minus the absolute value of gamma 1, -3/5, which is just 3/5 squared. And the absolute value of gamma 2 is also 3/5. So we're just going to square this entire equation. And that becomes 0.4096. And the question asks how much power in percent is being transmitted. So to find the percent, we need to multiply this by 100. And that gives us 40.96, and we're going to round that to 41%. So that is the power being transmitted all the way to the other end. So the next question asks, what is the wavelength in glass? So number 4, the wavelength specifically in glass, we know the wavelength equation is 2 pi over k. But because this is specific to in glass, we need to take our k that was calculated from the index of refraction with N2 equal to 4. So if you look back up here, we calculated our first k with taking into account the index of refraction of 1 in air. However, since we want to find the wavelength in glass, we look to K2, which uses our index of refraction of 4, which was in glass. And so K2 is what we want to use in this equation. So I'm going to go ahead and write that K2. So 2 pi divided by K2 was 1,333. and that equals 0.0047. And that is 4.7 millimeter. So going back up to the top, so that is our wavelength in glass. Question 5 is, what is the wave impedance in the glass? So question 5, the wave impedance is eta, and again, specific in glass. So this is equal to eta naught divided by n, as we said earlier. Eta naught is the wave impedance in the vacuum, so that's 377 ohms. And index of refraction, we have 2, but we specifically want to know what the wave impedance is in glass. So we use the index of refraction in glass, and that was 4. So that is equal to 94.25 ohms, unit of impedance. So that answers all parts of this question. Key things to remember here are, when you have a reflected wave, it's going to be propagating in the reverse direction, and the right-hand rules can be very helpful when trying to find your coordinate directions as well as creating relationships between EH and K. So with that being said, I hope this was helpful. Good luck in 140.